So good day everyone. In this video we are going to discuss the open circuit fault. So like in the short circuit fault, the formula was derived based on the symmetrical components, and here in the open circuit fault we are going also to use the symmetrical components to analyze and derive the formula of the voltage and the currents during the open circuit. So for the open circuit fault, there are two types: the one line open and the two lines open. So one line open and two lines open. Okay, so these are the two types of open circuit fault, and we are going to apply the symmetrical components. So this is the formula for the sequence currents, so and also for the phase currents. So for the voltage, they are the same, just change the I into V. Also here, change the I into V. And for the phase voltage also, just change the I into V. Also change the I into V. Okay, and also for the sequence networks. So these are the sequence network. So this for the positive sequence. So this is the equivalent circuit, and for the negative sequence, and also for the zero sequence. And this was already discussed in our first video. Now these are the tools or the symmetrical components that we are going to use in analyzing these two types of fault, the one line open and the two lines open. Okay, now first we are going to analyze and derive the formula for the one line open. Okay, so assuming we have a balanced three-phase system, okay, so let's say this is phase A, phase B, and phase C, and the phase currents IA, phase current IB, and phase current IC. Okay, now let's assume that one line is open, assuming that phase A is open. Okay, so let's assume a dotted line. Okay, so assuming that the phase A is open, so therefore by analysis, phase A is equal to 0, right? So because there's no flow of currents. And how about the voltage? The voltage, let's say this is VA, this is VB, and this is VC. Okay, now here VA, since there's this is an open, so there is a voltage between this open circuit. Okay, so this is called the series voltage. So there is a voltage, but VV, since this is not faulted one, VV is equals to 0. VC also is equal to 0. Okay, now we are going to use the the symmetrical components. Now for the phase A, since phase A is equal to 0, so from the symmetrical components, the formula is equal to I0 plus I1 plus I2, right? So therefore this is equal to 0. So this is our equation 1. So how about the voltage? Okay, so if we will use the symmetrical components, the voltage sequence voltage formula is 0, V1, V2, 1/3, 1, 1, 1, 1, A squared, 1, A squared, A, the phase voltage VA, VB, and VC. Okay, we'll use this formula. Now, since VB and VC is equal to 0, so this is 0, this is 0. Now, by multiplication of matrices, this will become B0, B1, B2 is equal to 1/3. So VA times 1 is VA, VB times plus, this is plus VB times 1 is, since VB is 0, so this is 0, plus BC times 1, but BC is 0, so this is 0, right? So next, multiplication of matrix in the second row, VA times 1 is VA plus VB, but VB is 0, so this is 0, plus BC times A squared, so this is 0. Next row, VA times 1 is equal to VA plus, but VB and BC is 0, so this is also 0. Okay, so therefore B0, B1, B2 is equal to 1/3 VA, VA, and VA. Okay, so therefore V0 is equal to V1 is equal to V2, which is equal to 1/3 VA, right? So they are equal. Okay, then if we will use the sequence network, the three sequence network, so therefore if this is a positive sequence, so this is B1, B1 is here, so therefore the negative sequence, let's say this is negative sequence, this is Z2, is, since this is they are equal, meaning they are connected in parallel, so this is positive, negative B2. The same with the zero sequence. So this is Z2. They are connected in parallel. This is V0. Okay. So it complies the derived formula that V0, V1 is equal to V1 and V2, which is equal to 1/3 VA. So now, since this is the current I1, this is I2 and I0. Sorry, this is Z0. Okay. So therefore, the interconnection of these three sequence networks is this one. So next we are going to derive the formula. Because we are going to calculate the sequence currents. Then after that, we will use the phase currents in the symmetrical components to resolve and determine the phase currents during the one line open. Okay. Okay. Now, since in our analysis, the interconnections of the sequence networks is this. So, meaning, if we will use the symmetrical, the positive sequence network, so the equivalent, if we will assume the equivalent of this, let's say this is ZOC or open circuit. The equivalent of that is the parallel of this negative sequence and the zero sequence impedance. So therefore, Z0C is equal to the parallel equivalent Z0 over Z2 plus Z0. So this is Z2C. So therefore, it will be if we will simplify, it will goes like this. This is now the ZOC. Okay. Oh, meaning during one line open, these three sequence networks are interconnected, and by using the positive sequence, we have only because since as we know that the positive sequence, this is the actual impedance diagram of the power system, right? So meaning, if there is an open circuit, one line open, so you have only to insert the equivalent parallel impedance of the positive of this negative and the zero sequence impedances. So now the simplified diagram is this one. Okay. Now, since IA is equal to 0, IA is equal to 0, which is equal to I1 plus I2 plus 0, I1 and I2. Okay. And I1 is equal to negative I2 plus I0, right? So this is our equation 2. Now, for the I2, I2 and I0. So from the sequence network, before the open circuited happens, so they are uncoupled. So meaning from the sequence network, the negative sequence network. So this is Z2, positive, negative B2. Okay, this is I2. So from Ohm's law, the sum of the voltages around the loop is equal to 0. So therefore here B2 plus I2 Z2 is equal to 0. So therefore B2 is equal to negative I2 Z2. Okay, and for the zero sequence, this is Z0, Z0. So the same, the sum of the voltages around the loop is equal to 0. So B0 plus I0 Z0 is equal to 0. So therefore B0 is equal to negative I0 Z0. Okay, now since B1 is equal to B2 is equal to B0, right? So therefore this two formula, if we will equate that, this will become B2 is equal to negative I2 Z2 is equal to B0 is equal to negative I0 Z0, right? Therefore this will become positive. So if we will take the I0 is equal to I2 Z2 over Z0, right? Okay, therefore if we will substitute this in this equation, I1 is equal to negative and I2 plus I0 is I2 Z2 over Z0. Okay, so therefore if we will multiply both sides by Z0, so this will become Z0 I1 is equal to negative, so this will become I2 Z0 plus I2 Z2, right? So therefore I1 is equal to, or I2 is equal to negative I1 Z0 over Z0 plus Z2. Okay, okay, and so this is now the I2. So this is 3. How about the I0? For the I0, we have the formula here. Okay, this one. So the I0 is this one. In terms of I1, so it will use this formula. I0 is equal to it will substitute this into this formula, so this will become negative I1, and see this one, this will become okay. First we will Z2 over Z0 sorry. So this will become I1 negative I1 Z0 over Z0 plus Z2 multiplied by Z2 over Z0. So this will become cancelled. So I0 is equal to negative I1 Z2 over Z0 plus Z2. Okay, so these are the equations of the sequence currents. So this is okay. It will summarize. So now it will summarize now. So this is the equivalent interconnections of the sequence networks for the one line open, and the formula for sequence currents or the zero sequence currents is this one, and for the negative sequence currents is also this one. Then the equivalent parallel impedance of this Z2 and Z0 is equal to ZOC, right? So therefore the I1 now will become by Ohm's law in this diagram. So I1 is equal to the voltage source VG, let's say this is VG over Z1 plus ZOC, where ZOC is the equivalent impedance, the parallel impedance between the negative and the zero sequence impedances. Okay, so these are now the formula for the currents during the one line open. Then once you calculate the value of these three sequence currents, then you can calculate the applying again the symmetrical components formula. This is 1 A squared A 1 A squared. So you have to substitute that here. Then after that you can determine the value of phase currents. But since this in one line open, and we assume that phase A is open, so this IA is equal to 0. So you have to determine the value of IB and IC, and you have to compare that in the line currents, the phase currents before the the one line open. So you have to compare what is the value of the phase currents between before it is opening and after it is opening. So that's all for this video, and thank you guys, and God bless.